Bessie, and I'm the lead in the IESO project for pale blue hydrogen. We have one milestone, which is a feasibility study for the demonstration of production of pale blue hydrogen and capture of carbon dioxide by microalgae.
And this is our integrated system, and we're using this everything supported on the solar panel, and we're going to split methane into hydrogen. Okay, so this is our system and the plasma reactor system.
So to simulate the main composition of biogas, we use two gas cylinders, one methane, one CO2. We mix them together. We mix it here, and then the mixture gas will go to our first separation membrane. After the membrane, the CO2 will come out from the permeate site, go to recycle to another device for the application, and the separated methane will come out to our buffer tank. There's a back pressure regulator. We can control the flow rate, and from the buffer tank, the pure methane will go to the plasma reactor, controlling the flow rate by the mass flow controller. After the reactor, which part will be talked by another people.
And this is plasma generator. It will provide voltage and energy to produce plasma, and this region and plasma species will react with methane to produce hydrogen, and we receive hydrogen and unreacted methane to downstream.
And we have some unreacted methane that also comes out. We send it to this second membrane module, which extracts the hydrogen that we can send for storage and later use. And the remaining unreacted methane, it then cycles back through the plasma reactor so that we can get a higher yield utilization of that methane.
Okay, so here we are in the Pale Blue Hydrogen Project, and we're looking specifically at the small scale green hydrogen. So Giorgio, what's going on here? What are we seeing?
So here we have 3 solar panels connected to this small AEM, which is a smaller version of the one that Safer Neutron and Kwame are powering in the pond. And we are converting the solar energy through a DC to DC converter directly into the electrolyzer and converting the energy into hydrogen.
And so that's a really important point. So on the larger system, we converted the power first to AC and then back to DC. Yes. We automatically lose efficiency that way. This is a much more efficient system, and it's running off of an open source DC to DC converter. So how do you collect the hydrogen then? How do we know we're getting good, pure hydrogen from this system?
So we have gas bags that we are collecting hydrogen with, and this gas bag, after the hydrogen has been, the gas has been dried, is being collected, and then we are here to test it with micro GC to see the purity and the composition of the gas. And so yeah.
So here we are in part of the Pale Blue Hydrogen Project, and we're looking at the photobioreactor that we use to take all of the excess waste carbon dioxide and convert it into microalgae that then can be turned into food or to plastic. So Max, what does this photobioreactor do?
So this is a vessel that can grow algae inside. As you can see from the LED lights on the side, this supplies the needs for algae photosynthesis. And we have a motor to stir the medium to encourage the growth. And the component over here is to measure the optical density of the algae growth inside, so we can know when to harvest, like how much it has grown. And we have the measurement for temperature, measurement for pH, and measurement for how much oxygen has dissolved inside. We are also have an air outtake, since we are growing medium inside, and then we are intaking CO2 and oxygen this way, so the pressure doesn't build up inside.
So Max, how did you manufacture this system?
Most of the parts on top are 3D printed, and then the glass vessel is of course bought off shelf, and all of the components are uploaded into an online repository, so anybody who has access to the internet can basically replicate the entire build.
One of the particularly unique features of this open source photobioreactor is the control system. So it's a full SCADA system. You have control over everything Max just mentioned, and you're able to data log. And so our control system is called Bread. It's made up of individual slices, which are boards that each have a specific function. Say, for example, monitoring the pH. And so, Max, can you demonstrate how you're able to control the bread-based photobioreactor using just a simple web page?
Yeah. So as you can see, the system is already running, and then we have set the stirring motor speed to 50%, and then sampling pump speed, which is the blue one over here, to 80%. And over here, user can input anywhere from 0 to 100. For example, I can put 0, and after the system responds, it should stop the motor from spinning. Yeah, as you can see, it just stopped. And similar to the sampling pump, I can do that as well. So it's normally suggested to take the sample when the motor is not running, so that you are taking a sample that's more representative to the growth of the algae.
Our sub-milestone is capturing the CO2 which is generated in the blue hydrogen part, which is the plasma reactor, where we split methane into hydrogens and CO2, and then we separate the CO2. The CO2 is then captured by the microalgae.
Here it's a demonstration of our 20,000 liter microalgae cultivation system. The goal of the harvest all the carbon dioxide generated from the hydrogen production into this microalgae, turning it to the biomass, which will be, as Dr. Bessie explained, will be transformed into a bioplastic. This is a growing large scale cultivation system. We have a very efficient harvesting system that will be attached to this to harvest the microalgae, concentrated, and then eventually turn it into a microplastic.
We have microalgae in here. The strain that we're using is Chlorella vulgaris, and the CO2 is coming from that system to our system. Also, the power is provided by these solar panels here. We need that power for the mixer and other stuff. And the nutrients, for now we are using plant food, which provides the nitrogen, phosphorus, and other elements that microalgae needs for its photosynthesis process and its growth.
So let me also ask you, once we grow the algae, how are we going to separate the algae from the bioreactor and recycle the clean water?
So we have some hollow membrane, the filtration, that the pore size are just smaller than microalgae size. So we can just do it continuously. We can separate microalgae cells from the media and then return back the media into the bioreactor again.
And we have demonstrated that in a smaller 600 liter scale.
Yeah.
The recycling of the clean water.
Yeah. We tested that system in a smaller scale in 600 liter photobioreactor that we have in the other lab. And then we use that microalgae also as the inoculum for this larger system.
Yeah, so in general, we have demonstrated the feasibility of capturing CO2 generated in the blue hydrogen and overall in the pale blue hydrogen project.
Yeah.
Welcome to the largest floating photovoltaic array in Canada. We're here with PhD student Kwame to talk a little bit about floating photovoltaics. Hi, Kwame.
Hello.
So what is the system that we're looking at?
So this system is a 7 kilowatt foam-based floating FPV system. And this is the first of its kind. And the advantage of this system is that we're using a very flexible and lightweight PV module.
Excellent. So I can see that it looks like it can ride the waves. Is there some advantage to having a flexible module on the water?
Yes, there is some advantage of having the flexible modules on the water, because this is not the first floating PV in the world. But this is the first one that is using flexible PV modules and a new technology using foam as the floating material. And this allows us to reduce the cost of the system.
Excellent. So the systems cost less because your balancing systems is basically just foam. What about the environmental aspects? Is this good for the environment?
So for an environmental standpoint, we've been seeing that the system is integrating very well into its natural habitat. So we've been using like wood as a supporting material, which will eventually degrade in the water with age, and we can just replace it instead of using plastic.
And then one thing that we've noticed too is that the fish actually love having the shade. So during the very hot days, they like swimming under the module instead of being directly under the sun. And then furthermore, what we've been doing, since we're using foam, we're running testing to see whether that foam is generating microplastic in the water or not. So before we've installed this, we've already taken sediment samples in this pond that we will be analyzing to see what's the baseline of microplastic in the water. And then every year we're going to be taking new samples and then analyzing them and looking at what kind of microplastic has been generated, and then doing an IR analysis further to see if that plastic is coming from our foam or not.
So I've noticed, like, today it's a really hot day. It's like record temperatures because climate change is even impacting us here in Ontario. How do the solar panels feel about high temperatures?
So usually solar panels, they do like the sun, but they don't like the heat. So when a solar panel is like in the desert area, for example, they will be generating less energy than they will do on the same day and same condition if they were in a colder environment. Because they are on water, we have already been seeing that there have been like a water cooling effect on the modules, and those effects we will be quantifying. So if you see all those tubes that go into that box behind there, those will be our temperature monitoring of both the water temperature and the PV temperature. Then we'll be also having sensors to monitor wind speed, air temperature, relative humidity, and with all those we're going to be showing and confirming further what has been done in the literature to show that the water is having a cooling effect on the PV.
So with that cooling effect, we'd expect to see higher efficiencies, more energy coming out for the number of power units that you have installed, right?
Yes,
yeah, and then from so I'm understanding that you might have run a life cycle analysis on this type of technology. How does this compare with, say, a standard photovoltaic array that you put on land?
So from our first result that we got from the life cycle analysis, this has actually been shown that this system has the potential to be the greenest type of solar PV ever. So the reason being, we're using no concrete for foundations. The foam, even though in our analysis we've run the foam to be changed every 5 years, this system still beat all other PV systems. And knowing that all other PV systems are already more environmental friendly than the traditional type of energy generation, this definitely has the potential to be very good for the environment and for the energy generation.
Oh, excellent. So I know, so we've put out this system here, and I noticed that there's a bunch of blue lines running to the individual modules. So what are those for?
So those blue lines, right now during the summer, we have no use for them yet, but once the winter comes, that's where all the fun begins. Because we're in Canada, during the winter, it snows, it gets super cold. This point, the very small point, is going to freeze. So how are we going to keep those PV modules from degrading or from being damaged during the winter? So these are what the blue lines are. We've already run an analysis for the last 2 winters on a smaller pond, sticking the PV modules on the pond and just letting them freeze. We've already seen that the degradation is very slow even when no precaution is taken, but we want to keep them running for longer. So those blue lines are air lines that are powered by a pump inside that box, and in winter we're going to be pumping air around the modules, and the fact of moving the water is going to prevent the formation of ice, extending the lifetime of the system and also allowing the system to actually generate more energy during the winter.
To the best of our knowledge, this is the only FPV array in Canada at all, and the unique aspects of the flexible solar panels being mounted on foam with air bubbling thereby allows you to actually have it year-round. And the only other systems we're aware of are right on the other side of Icy Park here, which are the ones that you built before. So can you talk a little bit about the electrical design of the system that we're looking at?
Yes, so for this specific system, we decided to go with 4 different arrays. So you will see that the system is grouped into 4 different parts. That one we call array 1, array 2, array 3, array 4. And each of them has their own power tracking from the MPPT inside the box. And we do this because since this is an experimental system, we want to have the flexibility of turning one of the system on and off and being able to run multiple experiments in each of them. So the way this system is set up, we are able to run 4 different experiments at the same time because they have different controlling units. So the way we wire them is we have them in series. So those one there are all in series and then in parallel, and that allows us to have a 48-volt system inside our box with the batteries, and then the whole system is a 7 kilowatt system, and this amount of power is more than enough to power a residential house here in Canada.
Excellent. Well, thank you very much.
Thank you.
Just as we saw on the large FPV system on the large pond, we have a synthetic pond here that we did some of the preliminary experiments on. So, Kwame, can you walk us through what's going on in this pond?
So this pond is a little version of what we have in the big pond, where we have 3 PV module, 110 watts, connected here to a charge controller, a battery, and an inverter. So this is the first one that we did. So it's the first foam-based FPV ever in the world, in a cold region. And what we did here was that we connected the PV module, installed them on this pond, and we have let them sit here for 2 winters already, and we've been collecting data over them. Right now the cameras are out in the room to collect the data, but we had 2 cameras here and there to actually look at the ponds to see what's been going on as the weather changes.
And so over the course of the winter, when the pond froze, how did the FPV array do?
So you can see there we have another PV system. So that one here is our test PV, where we have no air bubblers running on it, and here we have the main PV with the air bubblers running all over it. So what we've seen is that during the winter, when we pump the air from the air pump inside the water, right after a snowstorm, both PV are covered in snow, but the one with airs clears in about half of a day once the sun comes out, which shows us that like pumping air inside the water, even non-heated air, the movement of the air allows the PV to prevent ice formation very quickly.
So this small FPV array is going to be used to run one of the pumps for the Pale Blue Hydrogen project, specifically focusing on the blue part of the hydrogen in order to be able to get pure carbon dioxide and methane from a mixed system. All right, so here we are again at the FPV array here at Western, and we have enough power on the water to power a home. But what we have behind us is a really intricate industrial power system. And so to explain this today is Mona Kabir. So hi Mona Kabir, thank you for doing this.
Thank you, Professor.
We got a lot of wires, a lot of electronic boxes. How do we get industrial power out of a pond?
As you already know, like the PV system is 7 kilowatt, and at that level of power, the system that we need to build, the battery system, is like 48 volt. So we went for 48 volt system. So we have 10 kilowatt of battery here, which is charged by 4 different MPPTs. We could have done it with 1, but we went for 4 because like it's an experimental system and we want to monitor all the arrays differently. That's why we went for 4 MPPTs, so we can monitor those PV generation data from each array.
So very quickly, what is an MPPT?
This is a charge controller which charges the battery from the PV, but it's an intelligent system that always optimizes the maximum power from the PV.
All right, so then we've got DC power coming in from the PV. It makes sure that we're getting the maximum amount of power from the solar panels, and it's being stored in the battery. Then what happens next?
Yeah, so the requirement for the electrolyzer was DC, but for that level of high current that it consumes, so we have to go to AC solution of it. So we went here. We made a 3-phase system out of 3 identical inverters, which are like made by Victron, and then we synchronize them in such a way that they coordinate with each other and operate as a 3-phase unit, and then they supply this power to the DC power supply for the electrolyzer.
I noticed that there's another. It seems like there's a smaller inverter here. What's that one doing?
This is like although we went for 3-phase for the electrolyzer, but still we have some pumps in the electrolyzer system which operates on 110 volt. That's why we had to go with a small inverter. And also, if you already see the photovoltaic system, it has pump in it. Those pushes air into it to prevent ice forming. So to power those pumps, we have 4 pumps here for each array system, and those are also getting power from these small inverter single phase.
And so, to the best of your knowledge, are doing 3-phase off-grid systems like this a common thing? Like, where would this be done?
It's not common for residential, but for, of course, for larger scale implementation of PV or even the PV plant, they go for 3-phase inverter mostly. And if also they always go for 3-phase grid connected inverters. But if you want to charge your battery, so you have to go off grid. So this kind of inverter can help you that. And also if anyone wants to like generate hydrogen or this kind of large load off grid, they can adopt this solution. And yeah.
Okay. So for this particular application, we're trying to drive a large AEM electrolyzer. And so because of the power supply that we had available to us from our partner Cypher Neutron, it had to be converted to AC power first. If you were going to do this project in the future or scale it up, what would you do differently than what we've done here?
Yeah, the plan would be to connect directly the DC power to the electrolyzer, because the electrolyzer takes DC. So without losing any efficiency while converting DC back to AC, and then vice versa, we can directly supply this power using a DC to DC converter.
And that's what we've demonstrated at the smaller system, which we'll be seeing in a moment. Okay, so here we are with the largest FPV array in Canada, running Cypher Neutron's latest prototype of an AEM electrolyzer. So, Moda Kabir, what's going on here? What do we see?
As you can see, this is a stack of AEM. It has 27 cells in it, and it operates usually around 48 volt, and it can operate up to like 150 amp. But for this experiment, we're gonna go until 100 amp.
And so the power supply that we talked about before, where we're running 3-phase AC electricity, first goes to this gray box. What's that? What's it do?
This one converts the AC, 3-phase AC to DC, and it's a variable. It can supply up to 50 volt and 200 amp.
And then the power supply that's next to it, what's it doing?
Okay, as you can see here, there are like 4 pumps, and they are grouped in 2. And these 2 pumps, which mixes the electrolyte from these 2 tanks, and those 2 pumps circulates the hydrogen and oxygen. And those are powered by that small power supply, which operates on 110 volts.
Kwame, could you walk us through where is the electrolyte and the water going, and what's happening to it as it moves?
So what's happening here is that we have electrolyte both in this tank and that tank. To start the system, we first need to run these 2 pumps, as Moda explained, which are going to first mix the electrolyte because maybe it has been sitting and needs to be mixed between both containers. Then after that, we run this pump to start circulating the electrolyte in the system, but no reaction will be happening yet. So the reaction happens from the moment we power up this power supply. So this power supply is totally off-grid here, being powered from the PV box, and then once this power supply is powered up, it will convert the 3-phase AC electricity into DC electricity, which is sent then to the electrolyzer here, having the positive side connected to the oxygen tank and the negative side connected to the hydrogen tank. So what will happen once this electrolyzer is powered, when the electrolyte comes here, the water in there is going to be split here into both hydrogen and oxygen.
So the electrolyzer that we're using here is an AEM electrolyzer from Cypher Neutron. So that's different than the common electrolyzers you see on the market. So what's different about it? What makes it special?
There are 2 things that I need to mention here, how it is better. It's like, first, it has a membrane in it, so it stops recombination of the splitted ions, and that's why we get more efficiency out of this inverter. And the second thing is that it can handle any variation of power very quickly. That means for this one, it can ramp from 0 amp to 100 amp in very quick succession, and that's very important to deal with such a supply like PV, which nature is variable. So this can adapt that very quickly unless any other electrolyzer present in the market. So that's why we went for it, and this is the better solution.
Sorry. even on a sunny day like today, you still have some clouds, and that's going to give you a variation in the photovoltaic power that you have. And so to directly run an electrolyzer, having an electrolyzer that can handle those fluctuations without decreasing its efficiency are extremely important. And so the other very important thing about this electrolyzer is that the hydrogen content coming from it is extremely pure, and that's because of the membrane system in the AEM.
So once the electrolyzer has been powered, the water or the electrolyte coming inside of it is going to be split here into hydrogen and oxygen. And then once that split happens, these two lines here are going to be sending that hydrogen and oxygen back into the tank, and then those gas that have been produced are going to be taken out from these two outlets. So this outlet here is going to be taking hydrogen out, and this outlet here is going to be taking oxygen out.
And this hydrogen is green hydrogen. It is only being produced by the power of the solar cells. There's no carbon dioxide being created whatsoever. In our pale blue hydrogen project, this is what gets us the green hydrogen. So in the green hydrogen setup with the Cypher neutron AEM electrolyzer, we don't have really any moving parts. The pumps are simply pushing fluid. So how do we know that this is actually working?
So after the electrolysis is done, the gases are separated. This is the gas line for the hydrogen, and this is the gas line for the oxygen. So to see that whether it's hydrogen or not, there's a...
Stop.
This is the green hydrogen for our pale blue hydrogen project. All of the power that is being used to convert water into hydrogen is coming directly from the solar cells, so it's completely green. There's nothing moving in there other than the pumps to move the fluid around, so there's really no evidence that hydrogen is being produced. So Sarah, what can we do to show that there's hydrogen?
Yeah, that's a very easy technique. So since like after the electrolysis is done there, two pipes are separated, which will eventually have oxygen in one and hydrogen in one pipe. To see that this is really collecting hydrogen, we will just put the pipe into the KOH solution, and here you can see that there are bubbles coming out. So that means that it gives us the proof that hydrogen is generated, since we can see the bubbles here.
And the data that we have from Cypher neutron, we have very good data on the flow rates and the purity of the hydrogen.